Hi, my name is Jason Harlow. Welcome to my V Office Hour. I'm going to go over the solution for Physics 132H1F Fall 2009, Test 2, Version 1, Problem 3. This is a question based on Chapter 29 of Knight's Second Edition on the electric potential, and in particular Section 29.1, which is electric potential energy. So first, let's carefully read the question. A proton is released from rest at the positive plate of a parallel plate capacitor. A vacuum separates the two plates. The proton crosses the capacitor, and just before it hits the negative plate, it has a final speed of 1.0 times 10 to the 4 meters per second. What will be the proton's final speed if the experiment is repeated with double the amount of charge on each capacitor plate? And there's a list of 5 choices of final speeds, all in meters per second. Okay, so can you picture it? You've got a positive plate and a negative plate of a parallel plate capacitor. They're equally and opposite charged, and you have a proton released from just near the positive plate at rest. It's repelled, so it's going to fly over and be going some final velocity just before it hits the negative plate. And we're asked what would happen to that final velocity if you doubled the amount of charge on both plates. Now generally there's 2 ways of doing these kinds of questions. One is the force method, where you could compute the electric field and find the force on the proton, and then use Newton's second law to find the acceleration and go through and track the acceleration as it goes from one plate to the other. And the other way is to use conservation of energy, to compute the energy initial and energy final and set them to be equal. That's the way we're going to do it in our solutions. So let's take a look. Okay, so taking a look at the solutions here, we have, let's first draw a diagram. Here's the positive plate with some electric potential, V initial, for the proton, and then here's the negative plate with some final potential for the proton, which is going to equal 0, because just by convention we always set the negative plate to have electric potential is 0. So we're going to use conservation of energy here, and I've written this out a little more carefully. The total initial energy equals the total final energy, and for a proton, which is neither moving up nor down, so there's no gravitational potential energy, the situation is we have kinetic plus potential, where the potential, the kinetic is 1/2 mv squared, and the potential is q times v, where v is the electric potential and q is the charge of the probe, in this case is the proton. So it's initially at rest, meaning the initial speed is 0, and finally it gets to the negative plate, which we define to have a 0 potential. So V, capital V final, electric potential is 0 volts, and plug that in. You've got 0 plus Q times the initial potential is equal to 1/2 V final squared plus, again, 0. So that's what we've written in the solutions. Rather quickly, here we are. And the question is, it's asking for what will be the proton's final speed if you double the charge. So we need to relate the final potential to the initial potential to the charge on the plates. So we're going to call that Q. So the final velocity, if you solve this, is 2 times little q times q over c, which is V initial, divided by m, the mass of the proton. So there's an equation for final velocity, and if the charge of the proton remains the same, the capacitance of the capacitor remains the same, mass of the proton remains the same, and you double the charge on the capacitor Q, then this will increase this whole right-hand side by a factor of √2, which is 1.4. So 1.4 times what it had before is equal to 1.4 times 10 to the 4 meters per second. The answer is C. So let's think about this. We've found that when you double the charge,
the final velocity is 1.4 times higher than it would have been. So what's going on is we've doubled the charge, so we've doubled the voltage between those plates, and we've doubled the voltage, so we've doubled the final energy of the proton. So doubling the final kinetic energy, we know that kinetic energy is related to speed squared. So we've doubled speed squared, so the speed has to be increased by a factor of √2. So it's the 1.4 there. So it seems to make sense. My name is Jason Harlow, and I approve this message.